as Mr. Bryden said, I'm a senior design engineer at Dyson. I work in the new product innovation department, which is coming up with the early concepts, so about 3 to 5 years ahead of production, working from sketches and then developing them into full products. I'm just going to talk to you a bit about the James Dyson Foundation, which is a foundation that's set up to encourage kids and people to go into engineering and design. And I'm going to talk a bit about how we do the design process and just walk you through the steps of why I became a product designer as well, and what the potential is for you guys if you're interested in going into design and engineering. So what is design? Well, design's about creativity and using engineering to solve a problem. Why did I go into design? Well, I have a vested interest in improving things, making things better, creating things. So when I was sort of 14, 15, I was interested in cars and motorbikes and started messing around in the garage, putting things together, and then doing design projects through school. And I realised it was sort of one of my strengths, so I decided to continue on through university, studied alongside Mr. Bryden, and carried on my career through. So as I said, the James Dyson Foundation is part of our company, or a subside of our company, that's set up and funded by Dyson to inject enthusiasm into producing young engineers in Britain. This is Sir James Dyson. I'm sure you've probably seen him on the TV. So he's my boss, essentially. And I'm going to tell you a bit about how he went about becoming the success that he is. So the James Dyson Foundation communicates 5 key points that James himself likes to communicate. Perseverance, being the underdog, frustration, wrong thinking, which I'll explain later, and perfectionism. Something that I'm not happy about in the presentation. So the first point, frustration. Why is frustration a good thing? Well, frustration is where design and innovation comes from. So if you think about something you get annoyed with in everyday life, for example, a dripping shower head, a wonky shopping trolley, something like that, it motivates you to do something about it, to take it to the next step, to redesign it, to rethink about it. And this is where James got his inspiration for his first major product, the vacuum cleaner. So James saw the standard bagged vacuum cleaner that got full up with dirt, clogged, lost all its suction, wasn't very powerful, was a messy thing to change around. And he thought, how can we make this better? One day he was walking past a sawmill in Bath, it's a timber factory, and he saw this big cyclone on top of it. And he realised it was separating the dust without using a bag, without using filtration in that method. And he thought, why don't I strap this onto a vacuum cleaner? So he went home and he built himself his first prototype. Now at work we see this image as quite an important image, and when new people start at our company, we sort of say to them, this is a great prototype, and everyone says, well, you've been studying at university, you've been studying at school, and you learn how to make really nice prototypes and make everything look really nice. And we say, this is one of our best prototypes. Why do we say that? It's because it's just such good resolution. It's about taking an idea and trying to make it work as quickly as possible using whatever means you have available. It's about focusing on the technology rather than the aesthetics at the start to make a product. Perseverance. So James wouldn't be where he is today without perseverance. Can anyone guess how many prototypes he had to make before he made his first vacuum cleaner, make it to market?
25.
Any higher?
150.
Any higher?
75.
Higher?
200.
Higher? Alright, getting closer. 5,127. So, shows how iterative the process is. It's about making mistakes, learning from them, going to the next level, going to the next level, striving until you get what you want.
Where did he store them?
Where did he store them all? Good question. I don't know actually. I think he had a big barn. We've still got quite a lot of them at work actually. Wrong thinking. Now, that might be a bit of a strange terminology, but what it means is not necessarily being restricted by your knowledge. So there's a quote from Albert Einstein there saying, imagination is more important than knowledge. And obviously you have to take that with a pinch of salt. But it just means that you can know stuff, but then you have to really imagine to take it to the next level. James did this a bit with his DC-01, the first product that was launched in the UK. So when he first tried to sell it to the market research people said people won't like the clear bin on. So the clear bin on our vacuum cleaners where you can see all the dirt, they said people don't want to see what you're picking up on the floor, it's dirty, it's horrible. And James sort of resisted this and said, no, I'm going to put it on the machine anyway. So he put it on the machine, and it actually became one of our strongest selling points. People were amazed at how much dirt was coming off their carpets. That's important because what it's telling you is that although market research can be valuable in design, it sort of says people only tell you what they already know. You have to almost prejudge what the consumer is going to want in the market. Does anyone know who this is? Yes, it says it there. Is that Thomas Edison? Well, it's Thomas Edison. He's the inventor of the light bulb, and he's a bit of an inspiration for us because we like to fail at work. He says, I've not failed, I've just found 10,000 ways that don't work. So we encourage making mistakes. Design is a process where you have to make mistakes. You have to design something, find it doesn't work, and then take a step back, learn from that. And if you think, oh, it might work, but it might not, try it. Try it, find out, see if it fails, see if it works. And then, you find some gems. Half these machines that we've developed from Dyson, for example, the air multiplier, have developed from other avenues of research. So we might have been researching the hand dryers, for example, that we do. And we've noticed how they whip water away, but then we realise how the airflow sticks to the surface or amplifies, like this air multiplier. This is where I work at the moment. Well, this was taken a few years ago. We're quite a bit bigger than this now. This is our research and development facility in Malmesbury in Wiltshire.
Where is it? What's the place where you actually work like? Where is it?
Where is it? It's in Malmesbury, which is just outside Bristol, down in the south. Yeah, and we've got about 1,000 people on site, about 450 of which are designers and engineers. In the department I work in, there's about 65 people at the moment. Really mixed, diverse group, and they're not just British engineers, they're from all over the world, loads of girls, loads of guys, really good cultural environment. One of our key motto is design, build, test, and that's a cycling process. So we start with the design, start with sketching, then we build something, and then we test it, and then we see whether we've passed or we've failed, and we'll go back and we'll do it again. And it all starts out with a brainstorm, so a thought cloud, I think we have to call it now. But so like you do in your lessons, if you're coming up with ideas in D&T, I imagine that you'll sit down in groups and you'll throw around ideas, and that's exactly what we do at work. So when we start on an idea, or we have a frustrating point we want to talk about, we'll sit down in a group of like 6 to 8 people, throw around some ideas. This is obviously about a gym or something, as an example. And we'll bounce off ideas off each other, and then start sketching. Now, as you can see, to be going into product design, you don't have to be an artist. So you spend a lot of time practicing all your sketches. A lot of design consultancies will expect you to be able to sketch very well. But when you go into engineering and design, the key is really the technology, the thoughts, the thought process. So this was done actually by one of our new product innovation directors, so one of the top guys in the company. And this is one of his original sketches of, it's just a valve, a simple valve system. but it was to communicate an idea, and the key is just being able to communicate it to other people, what your intent is. Once we've sketched, we then start to think, okay, let's start visualising this. So we use different techniques. Like I was saying before, you use what you've got available. Now we're a large company, we have a lot of resources available to us, but we still use modelling techniques such as card modelling, because it's fast. You can turn around something like that machine in about a day. So you can mock it up and you can take it along to a meeting, you can say, well, I think it's going to be this size, I think it's going to be this shape. And it's a really useful tool, and it costs next to nothing. It's a great way if you go into become a student in design and you want to create prototypes for your projects, then it's a fantastic resource to use. This was how the DC-16 started, so that's our first handheld that we made. This is part of it, so this is part of a later prototype. Now you can see that the shape has evolved quite a lot to this one. So those card models are good for a part, so they're great for getting an idea of size and shape, and then you'll start to add further resolution into the design. So you'll start to add weight and mass, and then you'll start to think, how does it feel in the hand? So you can't really get that from a card model, you take it to the next level. You can start playing around, we play around with plasticine, bits of metal to show where weight's going to be on a machine. Anything available in the labs. Usually at this stage it's really quick, so prototypes are taking sort of half a day to a day to make, and you take them back to the meeting and people talk about them. Cardboard's also pretty good for the Christmas parties that we have at work. Then you take it to a next level as well, and we start looking at the rapid prototype. Now I believe you've got some rapid prototype facilities here at college. We've got about 3 or 4 different types of rapid prototyping. These ones that you're seeing here is SLS, that's selective laser sintering. So you have a couple of lasers that come down and they converge and they weld the plastic, which is nylon in this case, together in a big bed of powder. And within about 5 days you can have sort of 300 to 400 pieces built up in this cabinet. It's our most commonly used one because it's most representative of the plastics that we use in mass manufactured products, so ABS and polypropylene. But that prototyping method is leading to loads of different avenues in design, and also into lifestyle choices. So rapid prototyping is going to come in more and more. It's already accelerating rapidly, but you're going to start seeing it probably in homes in the next 10 to 15 years. You can buy an off-the-shelf rapid prototype now for sort of £800 to £1,000 to have in your home, so that's about the equivalent of what a printer would have cost you 15 years ago. These are a couple of non-Dyson examples of SLS. One that particularly interests me on the left is this prosthetic limb. Now a company has started doing that because prosthetic limbs take about 6 months to make usually. These ones, they can scan an image of a person's limb, mirror it over and print it off, and within about a week they've got a working prosthetic limb, albeit maybe a temporary one. But it just shows how these types of facilities can be used for other almost more meaningful human-related issues. The picture on the right is currently the largest, I think it's just a graphic of the largest rapid prototype that's around at the moment. It stands at 3 meters tall, and they're looking at developing these for architecture. So in the future, possibly, your houses will be printed on big rapid prototype machines because they can print sandstone. I think it's this year that they're going to make a big 10-meter structure at an architecture show. So it's quite an interesting technology to watch. Taking it on from the conceptual stage, so where we've got the initial layouts of the machines, we start to pull more resource into them. So we start to build up our teams. So where we might be working individually, alone, we then start to make a team of like 10 to 20 people, because that's when it starts to become more complicated for mass manufacture. When you mass manufacture a product, you have to think about all the complexities of producing different components over multiple shots. So, for example, this plastic piece here will be producing 300,000 of them a year. there's going to be variation of them, and they have to fit next to the next plastic product. So it's really important that we work through all the problems, spend a lot of time being accurate in the design. The accuracy is communicated a lot in drafting, so computer-aided design, I'm sure you'll be getting on to computer-aided design soon, if not now. Traditional drawings are still used as well, so looking at 2D sections. When we start to build the machines up together, we can test a full machine that's fully prototyped. So this one here is a fully prototyped model of the DC-35. Does anyone want to guess sort of how much this would cost to put together in prototype materials?
£100.
500, a bit more than that.
20,000.
Close.
750.
It's more like it's £10,000 roughly to produce one of these. So this one will cost about £3,500. And the reason we spend so much, so we'll produce about 50 to 60 of those through the development of the product at £10,000 each. But the reason it's so expensive but so vital to spend that money at that stage is the next level is even more expensive. So when you start making the plastic parts, a machine like that will cost you about £4 million to cut all the tools. So you see why we have to sell large volumes to recoup that cost. It's also much better to make mistakes on those rather than spending £4 million and then making a mistake. Perfectionism. So part of design isn't just about drawing, isn't just about making stuff look nice, it's about making stuff work. So at work we have a lot of facilities to try and make our machines pass certain tests, make them good for the users. Just my own example of perfectionism is Lego. Now Lego is a really interesting product. They've got some of the most accurate plastic parts in the world. It's really useful. We use it at work as well to make prototypes with sometimes. It's quite good when you get to play with Lego. But they're really accurate. The design hasn't changed since 1948 on the Lego model. And they just click together. And only 1 in a million parts doesn't click together. So as I said about testing, this is some of our test facilities. They have to be incredibly accurate, so we use a lot of robotic testing. It's to get repetitive tests and also so that we can make claims. So when you design a machine that's going into the mass market and you have competitors, you have to work out how much better you are than the competitors. We always strive to be better than competitors. So you have to work out a standard, for example. We use pickup claims, so how much dust you can pick up off the floor, and then say how much better we are than the competitor. We test the SLS and prototype machines for destructive testing, non-destructive testing. This is showing like a high-speed camera, looking at the pickup on the floor, and we can analyse where the dirt's going. This is getting more into the engineering side of it. So you're looking in much finer detail and tuning your design now before it goes into production. Microbiology, we have a microbiology department. So again, you're not just looking at the design, you're looking at the surroundings of the design and how it's going to be affected in its environment and how the environment is going to affect your product. Acoustics are really important, so how the machine sounds. Not just how loud it is, it's the quality of the feel. So I don't know if you've all seen the VW advert on TV where they're shutting all the doors and they say how good their sound of their doors are, essentially. It's every aspect of the design coming together now. And then testing. So we also use human interaction testing. A lot of this gets done in Southeast Asia, so Malaysia and Singapore, which is where we produce our machines. And they test them to destruction. I think a cylinder machine like that will travel 10,000 miles on a bed before we say it's acceptable to release into the market. You can see them just stretching hoses around pillars and trying to break them, essentially. Because you want to know how robust your machine is. We guarantee our machines for 5 years, so we don't want breaking on people after 5 years. Then manufacture. So design is also about considering how your machine is going to be put together. We use a terminology called poka-yoke, which is a Japanese saying, and it's like the SIM cards in your mobile phones. So if you look at the SIM cards in your mobile phones, you know there's a triangle cut out of them. That's so they go together in only one orientation, and you have to think about that when you're designing a machine, because assembly time will lead to how many volumes you can produce every year. So it might be the difference between producing 10,000 and producing 100,000 if they're taking an hour to put them together or taking 30 seconds to put them together. And then the last point is underdog. So what I mean by underdog is not being defeated. There's a lot of large companies producing a lot of large machines out there. And James himself faced this when he was trying to launch his machine. So he had Hoover. They didn't want to buy his machine when he initially said, I've got this idea for a cyclonic vacuum cleaner. It's great. Do you want to buy it? They said, no, it will never work. People will never catch on. Anyway, he took it away and launched it, and it was obviously as successful as it is. And that sort of reiterates the perseverance point. But it also draws you to how important intellectual property is on a design. So as young designers yourself, it's good from the beginning to start recognising what patents are and what intellectual property is. So when I say intellectual property, it's about making a design your own and making it legally your own. So when you come up with an idea, you've got to date it, you've got to sign it, and then if it's a good idea, you want to try and launch a patent on it. So you get granted the fact that that belongs to you, and no one else can produce that apart from you, unless you give them your permission. So they're the 5 points I've taken you through. Second to the James Dyson Foundation, or part of the James Dyson Foundation, is also the James Dyson Award, which is a competition to go into. So if you've got a good design and you want to somehow launch it, take it through to the James Dyson Award. It's a competition. The best person in that year will get funding to develop their product, and that starts from sort of your age up, really. So remember that if you're going through A-levels and universities, we back people that have great ideas. You can also follow the James Dyson Foundation on Twitter. They give information to engineers going into university, taking it further, and how to